Physicists See the World. Course High School Physics. Level High School. Part 2. Time and space. Some questions seem far too simple to really care about. But it's often those questions that are the hardest to actually answer. What is time is such a question. Everybody believes that they know what time is. It's something you measure with a clock. But does time go equally fast for everyone? Could time stop? Could it go backwards? Does time have a beginning or an end? Is time just a flow of events? Or does time exist even if nothing happens? Let's look at how we measure time. The world is full of natural clocks, so to speak. These clocks come in the shape of periodic phenomena. Phenomena that happens over and over again, with roughly the same intermediary period in between. We've always used these types of phenomena to measure the passage of time. We measure year with the help of months, months with the help of the moon's phases, and days with the sun's rise and descent over the heavens. Hours, minutes, and seconds were brought in by the Babylonians 3,000 years ago. They probably devised the number 60 from your heart rhythm. 1 second was the time between two heartbeats in a healthy person at rest. The heart rhythm is an example of a biological clock. The first mechanical clocks weren't really invented until the 1200s. They had a pendulum that went back and forth. Today we use modern atomic clocks. They are so exact that they only speed up or slow down roughly 1 second in a million years. Right now we define a second with the help of the radiation from a cesium-133 atom. 1 second is the time for 9,192,631,770 shifts. The universe is very old, about 13.7 billion years old. The universe is so old that if you were to think of the entire age of the universe as just a single year, the Big Bang would have happened on the 1st of January. On the 31st of January, Milky Way and other galaxies would be formed. It wouldn't be until the 1st of September that our solar system would be formed. And it wouldn't be until the very last day, the 31st of December, that the last 40 million years would happen. Yes, the dinosaurs died out as recently as 1.5 days ago. The universe is so old that 1 second in the universal year would be 400 human years. Space. People have also wondered what space really is. Is the space finite or infinite? Has space always existed? Is space merely just a distance between objects? Or does it exist independent whether there's matter or not? Is it continuous? Is space itself something? Or is it simply nothingness? How many dimensions of space are there? Historically speaking, the human body and its anatomy was the place we started to get an idea of space. Length, to be exact. Measurements like inch and foot is still being used in a few nations. However, the vast majority of the world has gone over to the metric system. Today we use light to measure the exactness of 1 meter. 1 meter is the distance that light moves in a vacuum under the fraction of 1 divided by 299,792,458th of a second. The reason we can use the speed of light to calculate what a meter truly is, as long as we know what a true second is because the speed of light in a vacuum is a constant. It's always the same. Quantity, measuring number, and unit. When we write physical formula, we use letters as symbols for physical quantities. For example, we use a small t as a symbol for time, A physical quantity is made up of a measuring number and a unit. Imagine that you run 100 meters in 12.3 seconds. We write the result as t equals 12.3 seconds, or just an s. Mass and density. Both weight and mass is in correlation to the amount of matter that exists in an object. In everyday speech, we use weight and mass interchangeably. When you stand on your scale, it shows you the mass you have. But we usually call that mass number that you see on the screen your weight. This is actually erroneous. The unit of mass is usually kilograms, or just grams. The unit of weight is Newton. The weight of an object has to do how well the object is pulled by gravity. An object's mass exists regardless if there's gravity or not, and has purely to do with the amount of matter. Gravity becomes slowly weaker the higher up you go in elevation. So if you were to stand on a scale, you would find that you would weigh just a little bit less if you were flying at 30,000 feet, or about 10,000 meters, compared to when you were standing at sea level. However, your mass does not change, it's the same. It's just the acceleration of gravity that's weaker, the higher up you go. So remember, your mass is independent of gravity. Your mass doesn't change whether the gravity of the planet you're on is weaker or stronger. Your weight does, however. Mass has generally two properties that are very well known. One of them we've already gone through, that's weight, which arises between the interaction of mass and gravity. But mass also has something called inertia. This means that mass has resistance towards any attempt of changing its movement. For instance, if a block is perfectly stationary, you're going to need a certain amount of force to get it moving. Even if the block was suspended in space without any friction, you would still need a little bit of force to get it moving in a certain direction. This is what's called inertia. You would need even more force if the object was already moving in a direction opposite to the direction you're trying to get it to move in. The inertia would be greater in that case. Density is a property that is very important for us to keep in mind when it comes to physics. Density is defined as mass divided by volume. The symbol of density is usually the Greek letter rho. Mass usually is symbolized by small m, and volume is usually just symbolized with a big V. So you can write this formula as rho is equal to m divided by v. The density of water is roughly 1,000 kilograms per cubic meters, and the density for air is about 1.3 kilograms per cubic meters at sea level. However, density will vary very slightly depending on the temperature. There are three factors that primarily decide the inherent density of an object. It's airiness. Think of things like cotton. Cotton has, generally speaking, very low density because its mass is generally low and its volume is usually large because of air. The second factor is the average distance between the atoms of the object. Lead is very heavy, partially because the atomic nucleus has a lot of mass, but the primary reason why it is so incredibly heavy is because it has a very high density, which is due to the fact that the atoms of lead are very close to each other. This means that you have a pretty large value of m divided by a relatively small value of v. The third factor is the actual inherent mass of the atoms that make up the material. Uranium is very dense. The primary reason for this is because, well, the atomic nucleus of uranium has a lot of mass. It is the element 92 of the periodic table, and so the atomic nucleus of uranium actually has a higher mass than the atomic nucleus of lead. Alright, so let's try and solve some problems here. So let's start with the first one. So problem 1A. How many seconds in 24 hours? This one is really simple. How many seconds in 24 hours? Well, 1 minute is 60 seconds. And you have 60 minutes in an hour. So 60 seconds in a minute, 60 minutes in an hour. Then you have 24 hours in a day. They're asking 24 hours. So yeah, basically it's just, it's quite simple. It's 60 multiplied by 60, which is 3,600, and you multiply that by 24, and you should get 86,000, let's see now, 400, I believe. So yeah, in 24 hours, that's how many seconds you have. Now let's move on to question B. According to a table of values, there are 31,556,926 seconds in a year. How many 24-hour days do you have? Can you explain the answer? Okay. So the question is how many 24-hour days do you have if 1 year has that many seconds? Okay. So what we do is we take 31,556,000. Let's see, what was the rest? 926. So that's how many seconds are in a year. And now to find out how many days that is in a year, we simply just divide it with 60 seconds times 60 minutes. Oh, sorry. And 24 hours. And what we end up with is 365.24 days in a year. All right, so what's going on here? Why is it that we get this weird number? Because, I mean, we all know that we have 365 days in a year, right? Well, no, because every fourth year we have something called a leap year, where we add an extra day. And the reason is, a year is not exactly 365 days. It's roughly 365 and a quarter day. So in order to sort of balance things out, we add an extra day every fourth year, and roughly that works pretty well, actually. So that's really what's going on here. So that's how we explain this this number here. Our closest star system is Proxima Centauri, which is 4.24 light years away. How many kilometers is that? When the light reaches us from there, how old is it? Okay, so we're going to assume that space is a perfect vacuum. So, because in a perfect vacuum, the speed of light is constant. Okay, so a light year is basically how far light travels in a year. We know what the speed of light is in a vacuum. All right, so the speed of light in a vacuum is constant, and it's 299,792,458 meters per second. Okay, that's how many meters light travels in a second. Now we know how many seconds we have in a year, thanks to the previous question. So what we do is we take this and we multiply it with, so let's just multiply these, and so you get about 9 4.46 times 10 raised to 15 meters. Okay, now we need to take this and we need to multiply it with 4.27 because that's the amount of light years. So basically what we've just calculated, it's the amount of meters that light travels in a vacuum in a single year. Okay, so now we need to find out for 4.27. So we take this, which is about 4.04 times 10 raised to 16 meters. So that's how many meters Alpha Centauri is from us. In the question they asked for kilometers. Now 1 kilometer is 1,000 meters. So what you do is you just take this number and you just divide it, and you get 4.04 times 10 raised to 13 kilometers. Okay, so that's how many kilometers you have to go to get to Alpha Centauri, which is 4.27 light years away. Now the second part of his question was, how old is the light when it reaches us? And yes, this is a bit of a trick question. So this is a question that is asked just to see if you guys are paying attention. 4.27 light years is the same thing as 4.27 years, because it's how far light travels in a year. And so if it takes that long for light to travel to us, then the light is that old. So yeah, it's 4.27 years. Very big as well as very small physical quantities are easier to comprehend when we compare them with physical quantities we already deal with daily. So part A, Earth has a radius of about 6.4 times 10 raised to 6 meters. The Sun, 7 times 10 raised to 8 meters. How big would the Sun's radius be instead if we shrank both the Earth and the Sun to the degree where Earth only had a radius of 0.11 meters, which is 11 centimeters, which is comparable to a soccer ball? Alright, so let's solve this one. Alright, so the thing is, since the Sun and the Earth are shrunk proportionally to each other, the same amount, we only need to find out by how much more the Earth is shrunk to also find out how much the Sun has shrunk, okay? So the new radius of the Earth is 0.11 meters, and all we have to do is just divide that with 6.4 times 10 raised to 6 meters, which is equal to, which is 1.719 roughly times 10 raised to 8. Okay? So that's basically the ratio. So that's the new size of the Earth compared to the old size, okay? So all we have to do is just take this and multiply it with the older radius of the Sun, 7 times 10 raised to 8. What we get is 12.03 meters. And that's the new radius of the Sun. Wasn't so hard, was it? The hydrogen atom has a radius of about 5 times 10 raised to negative 11 meters. The atom has a nucleus with a radius of 1 times 10 raised to negative 15 meters. How big would the radius of the nucleus be if we enlarged the atom so it had the radius of half a soccer field's length, which is 100 meters? And half of that would be 50 meters. Okay, so what we do is we take the new value of the radius of the atom, 50, divided with the old value of the radius of the atom, times 10 raised to negative 11, I think it was. This is 1 times 10 raised to 12. Now we take 10 raised to 12 and multiply it with the old value of the radius of the nucleus, which was 1 times 10 raised to 15, negative 15. So 0.001 meter or 1 millimeter. Okay, so that should really tell you just how much empty space you actually have in an atom. So yeah, most of the atom is just empty space. That's pretty crazy, isn't it? All right, so let's move on to the next question. On a balance scale lies on one end a book and the other end 2 weights of 0.5 kilograms and 0.1 kilograms respectively. The scale is at balance. A, how much is the mass of the book? So yeah, how much is the mass of the book? Well, remember, this is a balance scale. So on one end of the scale, if the scale is at balance, the other end of the scale has to have as much mass as the other end, right? So basically all you have to do is to just put 0.1 plus 0.5, and that is 0.6 kilograms. And that's really it. It's not any more difficult than that. All right, so let's move on to B. B, the weights together weigh 5.9 Newton. What does the book weigh? Well, I mean, again, the scale is at balance, right? So yeah, it has to weigh the same. It has to weigh 5.9 Newton. It's that simple. On the moon, the weights weigh 0.97 Newton. What is the mass of the weights on the moon then? Yeah, so the question is, what is the mass on the moon? So the weight is different. Is the mass also different? And the answer is, of course, no. Mass is the same. Remember, the weight of something is going to change depending on the strength of gravity. But mass is unchanging. Mass doesn't change because of gravity existing or not. So mass is unchanged. Alright, so let's do the last problem. Alright, so let's do the last problem. A. An oak beam has mass 87 kilograms and the volume 0.12 cubic meters. What is the density? Alright, so this one is pretty simple. You just have to remember the definition of density, which is rho is equal to mass divided by volume. 7 kilograms divided by 0.12 cubic meters. And we get 725 kilograms per cubic meters. Wasn't really that difficult. B. A room has length 10 meters, width 6 meters, and height 3.3 meters. What is the volume? From the volume, calculate what the mass of the air in the room is if air has a density of 1.3 kilograms per cubic meters. Right, so we simply take the length multiplied by the width multiplied by the height, 198 cubic meters, okay? As we already know, density is the same as mass divided by volume, okay? Then we can easily find out what the mass of all this air is. Density multiplied with volume is the same as mass, and we get 257.4 kilograms. All right, and that's it. That's the problems for this chapter that we have solved. And the next video, we're gonna go through average velocity. So I'll see you then.